Hello and welcome to curl from start to end. This little presentation of mine that I am doing here on January 21st, 2025, here from my home in Sweden. We'll just start then. So curl does a lot of things. So my plan here today is to talk about, this is me first. This is me in my workplace. I work for Wolf SSL. That's my Mastodon account. Follow me there. That's my website. Everything about me. I do curl all day, every day, full time. Yeah, that's what I am. So today I'm going to talk about curl step by step, sort of from start to end. And the idea is to sort of not to learn how to type a command line. I've done a lot of talks and there's presentations you can see about, all the details about curl. You can in particular watch the mastering the curl command line presentation. But anyway, I want to show you what happens when you type a curl command line. Curl starts. There's a lot of things going on in between, and then it ends. And then I want to go step by step through all the high level things that happens when you from curl starts until it ends, and it spews out some download somewhere. And it is all based on an image I did a few years ago, that explains curl step by step in a single image, and I will show you that image, of course, and the presentation is around that, and we will end up with that complete image in the end. And there is going to be a Q&A, so if you have questions, and if you're watching this live and you're in the chat room, you can ask the questions in the chat room. If you're not watching this live, you can ask the questions on YouTube or contact me in another way. So the idea here today is to go through this particular command line. You enter in a shell or a command prompt somehow on your operating system, curl -v -O https://curl.se/index.html. And what then happens under the hood when you've done that? Well, you press return after you've typed all of this into the shell, and what happens next? So my illustration is going to be based around this image, and we're starting up here on the top left. That's the command line again. If we are unfortunate and someone did a serious bug, it'll just say segmentation fault and everything is done. No, seriously. So anyway, we start out with, of course, there's in a Unix-like operating systems, or in most operating systems these days, there's a dynamic linker that makes it search for curl in the path in your operating system. And usually in most Unix-like operating systems, Linux, it is installed in user bin curl, if you've installed it with a package manager, for example. And so the linker will find it there, and it will load all the shared libraries that this executable uses, which could be a whole bunch of them. And a lot of libraries, shared libraries, they use shared libraries themselves. So some libraries use other libraries, so there could be a whole bunch of them. If you check your binary on a Linux system with LDD, you'll see that in a typical Linux distro, the curl executable, I think, uses somewhere around 20 to 40 different libraries. But the key here, and what I'm talking about here today, the key library that's interesting for us here today is libcurl, of course, which is a very central and important library for curl, the command line tool, because libcurl is the engine library that will do all the network operating stuff for curl, the command line tool. So the dynamic linker will then start the curl tool, and load all the libraries, including libcurl. And then, so that's the first step. The dynamic linker will load those two, and it will start the curl command line main function, pretty much. So the curl main function, that's the main the first function really in the curl command line tool. It gets a list of all the command line arguments that the shell split up for us into a list, really, with all those a list with the options. So the first one is -v, the second one is capital O, the third one is the URL. As I showed you, that's the command line we get. So the shell, or we already get them split up like this, and the curl tool then just has a matter. Its task is to then, what do we do with this? What does it mean when we get a -v or a capital O? And for in the curl tool, then of course it converts these. In most cases, it just converts them over to a libcurl option or activity. So for example, if -v is used, V for verbose, then it means that it'll set the curl opt verbose option in libcurl. And -O means stored, whatever data we get, store it in a file name locally using the same file name as is used in the URL. So in this case, the URL ends with /index.html, right? So the file name part of that URL is index.html. So -O here means that we save the file in index.html. I mean the file, the data, whatever comes to us, we will save it. And as said in the chat here, it actually got the indexes wrong because argv0 is actually the tool itself. So it's actually should be 1, 2, 3 there. Anyway, I don't think it matters too much. And the URL then of course it sets the libcurl option curl opt URL. Basically, it converts all those input arguments into different libcurl options, and then of course it sets up libcurl, sets the correct options, and prepares to do the network transfer, right? So when it has done that, it'll call libcurl. Well, it basically called libcurl multiple times, but once it had set up all the options, it says start the transfer or perform the transfer, pretty much like this. So it loaded everything, it got the command line parser, it converted, checked all the input arguments or -v, -o and everything, convert that to libcurl activities, and then it calls libcurl. Libcurl then being the engine for everything network oriented here, or all the transfer related stuff. So libcurl gets an input, this is the URL we're going to work with, and libcurl itself then of course parses that URL. It has a URL parser, of course. So https://curl.se/index.html, what does it actually mean? It means that there's a host name that we want to work with called curl.se. There's a scheme on the URL, https, that says something about the protocol we're going to use, or we want to use. And since it is HTTPS and there's no port number in the URL, we're going to use the default port number for HTTPS, which is port 443. And there's a path in there, and the path is /index.html. So that's what the parser just splits it up into components. And of course, a URL can be way more complicated than this particular one. This is a really easy and straightforward one, and pretty short too, and easy to understand. So anyway, so that's what libcurl does first. Split up the URL into components so that we know what to do next. So once we have the components from the URL, remember we split out the host name. Oh, we want to work with curl.se. So curl.se, that's a host name, right? So we want to work with that. So what does it mean? So first we check, for example, that there might be an alt service cache that has information about that particular host name. Maybe the name is not there. And then we have a DNS cache. If we're going to do multiple operations, we might already have done a resolve of this hostname before. But in this case, we don't, right? So we checked the DNS cache. The DNS cache is actually empty right now. So we start a thread. And when it comes to name resolving in curl, there are a number of ways to do it, but the default way is to start a helper thread. And in that helper thread, we call get other info in a new thread to resolve the hostname curl.se. And resolving the hostname curl.se, of course, means asking for A and A quad A DNS resource fields for those. So it asks the resolver on your host. Well, it figures out the get other info function figures out who to ask for your DNS server basically, and asks the server for give me the IP addresses for curl.sc, both IPv4 and IPv6 addresses, and getAddressInfo will return those in a long linked list or a short linked list, depending on how many addresses you get. In this case, curl.sc, it has quite a few addresses, so I think you get 12 items in the list, typically 8 plus 4. So anyway, so once it's done, it just kills the resolver thread again, because now it's done. And it is a helper thread just to be able to shortcut it, to stop it, or sort of ignore it if we want to do that prematurely before the results are in. Anyway, so we stored the results then back in the cache. I told it was empty when we started. Now it's not empty anymore because we store curl.sc and the list of IP addresses for this hostname. And then we continue. Now we want to connect to the host. So we store, that's the thing then in here in the down right corner, we store the addresses, and I show you a few of the IPv4 and a few of the IPv6 addresses in that little box there. If you check it out, you'll see them for yourself. And those IP addresses are all IP addresses that you can connect to connect to the curl.sc HTTPS server. And once we have the IP addresses, we want to connect to that using TCP, maybe, or in this case, we go with TCP. So we have multiple IPv4 addresses and multiple IPv6 addresses, and we start the first connect attempt to the first IP address, IPv6 address in the list, and the port number from the URL 443, and we try a connect. And we send this TCP handshake, the SYN-ACK procedure, and if that fails, if the first IPv6 address fails, we can't connect to it, we try the next one in the list. And as I showed you, we have many addresses, so if the first fails, we go to the second and the third, and blah, 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 for every failure. And if it takes a long time, if it takes more than 200 milliseconds to connect to this IPv6 address, we start another IPv4 connect attempt in parallel at the same time. So if the IPv6 address connect is slow, we start an IPv4 one at the same time. And if that one fails, it tries the next IPv4 round. So we have sort of two connection attempts going on at the same time. And the first successful one wins, and the unsuccessful one is discarded. And I mentioned TCP, it says TCP on the top of the slide here, but if we would have asked curl here to try HTTP3, it would have done the same thing for quick as well, in parallel as the TCP attempts. So then it would have tried IPv6 and IPv4 at the same time. So a lot of different things happens here in a way to try to make sure that we connect to a working IP address pretty much as soon as possible, with a preference to the IPv6 one. And of course, if there are no IPv6 addresses provided for this particular host name, we don't try any IPv6 addresses, and vice versa. So it'll use what it has, and if we run out if any of those address families sort of run out, if they all fail, for example, if all IPv6 addresses fail immediately, we will of course start the IPv4 attempts right away, not wait for anything. So that's what we do then. We try that TCP connect, or we perform the TCP connect with this happy eyeballs sort of mechanism or algorithm, or whatever you want to call it. And happy eyeballs is this parallel attempt thing. That's the typical name used for that algorithm. And once we have done the TCP connect, we know that this is a HTTPS, right? We figured that out from the URL scheme, so we know that we are going to talk TLS over TCP. So once we have connected TCP, one of those addresses succeeded, so now we have a connection, a TCP connection, that's SYN-ACK thing. But now we also have to negotiate TLS on top of TCP. So then perform a TLS handshake. And in this TLS handshake, there's a particular field called SNI, server name indication, identification. I don't remember exactly. But anyway, it's a way to pass on the host name to the server and say, hey, because the server might serve a lot of different host names at the same time. So we say, we want to talk to this particular host called curl.sc because that's the one with the URL says we want to talk to. So we tell that to the target service, hey, this is the one. And we also fill in things like TLS versions, ciphers. We can negotiate a lot of things, including, for example, which I think let me get back to that. So we send the client hello, we get a server hello back, we send the client finished, server finished, all of these different things, which is pretty much TLS lingo to negotiate how we are going to talk TLS going forward. And we also negotiate which HTTP version we are going to talk once we are done negotiating. Do we want to speak HTTP 1 or do we speak HTTP 2? And we do that by using the ALPN extension in the TLS negotiation. Protocol, but I don't remember. Application layer protocol negotiation or something. So pretty much it allows us to negotiate which HTTP version to use with this particular server at this particular time. And then, including in this handshake, before we're done, we're not done until the server has said, here's my certificate. So that's included in every TLS handshake. So we get a certificate, and the certificate from the server is a signed blob from a certificate authority that is signed by someone that we trust, because it contains a list of which kind of names this certificate might be used for. So we verify then that the certificate we get back from the server is a trusted one. It is signed by an authority that we have in our CA store. And the names in the certificate also matches the name in the URL. And if it does, we can sort of move on. Then we have an established TLS connection. And voila, once we have connected with TLS, so that we're all good, right? So now we can do what we're here to do. We can ask for the resource. So in this case, I made it simple. Let's say we negotiated HTTP 1, or in some cases, if it doesn't negotiate at all, it maybe didn't even understand ALPN, then we go with HTTP 1 because it couldn't negotiate HTTP 2. We just stick to this. And we send a request, the HTTP request to the server, and it includes the path we want, the path to the resource we want to retrieve. And including in that request is also, again, the server name of the server we want to talk to, because, again, in HTTP it might serve many different names. And here you can see we already said the name in the SNI field, but we will say the name again in the HTTP request. And if there's a discrepancy there might be problems. But we don't have a discrepancy here because we talk with curl SC still. And we also say who we are as a user agent. And so it pretty much looks like this. We do a get of the path. We say we speak HTTP 1.1. This is our host name. This is the user agent. It's called curl 8. Could be whatever you want it to be. If you're doing this with a browser, it's going to be a very, very long string. It'll say Mozilla in there, and it's going to be a lot of different pieces of browser history in it. And that is how you ask for a resource over HTTP. So you send that over that TLS connection. This is what we want. We want index.html over HTTP 1. We are user agent curl 8. And when the server receives that, and if it is a HTTP 1.1 server, it'll sort of just figure out yes, we understood this, and we are going to send you back a response, and it'll say, here's the status code, 200 being okay, and it might say, in this case, in my example here, it says connection closed, which means it'll close the connection after this response. Typically, a server doesn't do that. But in this case, we send back 8,623 bytes of content, and our server is called something, version 21.1. The content type in this response is HTML, and then bloom, 8,623 bytes of data is delivered over this TLS connection. Ideally, hopefully, or that's at least the intent, right? And libcurl then parses these headers, of course, what they're called header fields these days, and make sure that it understands them, if it figures out. And in HTTP, there's a lot of different ways how to transfer when the end of the data actually arrives. So there are many different things that could change how we have to interpret this stream of data that comes from this server. But anyway, libcurl parses these headers, and once it starts to get data from the network, then you it delivers the data in callbacks to the curl tool, because the curl tool then has set up callbacks. So the callbacks are called one by one, or rather over and over and over. The callbacks are called and deliver data. So we're already now at the end, or not at the end, but at the left side here now. So we got the response headers. We're starting to get data, and when the callbacks are called in the curl tool, we remember that we had the dash capital O. It means save it in this file, index.html. So in the callback, it sort of figures out, here's the file name we want to use, and here's data coming in the right callback, and the right callback will be called over and over, and we just save it, open that file locally, and start saving data as libcurl delivers in the callback. We know that this is just 8K of data, so it's not a lot of data. It could actually work in a single write callback. It might be, depending on speed, you might get many of them. But it could also be, multiple gigabytes, and then the callback will be called many times, over and over and over, and it'll just save until libcurl says the transfer is done. And so also then there's this, if this transfer if it takes a while, there's also going to be a progress meter displayed, because the user might then want to know what's going on. So there's pretty much a built-in logic in libcurl that says if the transfer has been going on, I think it's pretty much regularly every second or so, it'll, depending on if you get data or how slow it is. So it'll update a little progress meter to show you how much data did it get, how fast is it transferring, and so on, so that you as a user can see that it hasn't died, or that something is actually still happening. So that's that. You continue with that then until the data is complete. And this can of course take a very long time, or it can be instant, depending on your network speed and the size of the data you're getting, or the amount of data that you're getting. So after that, once you've gotten all that data, all that 8K of data, it's time to shut down the TLS, because now we're done. And in this case, of course, we only specified a single URL, so there's nothing left to do here. We got that single resource, and now we're done. We won't use this server anymore. If you would specify multiple URLs on the command line, it could then now iterate over to the next transfer. And if you would have used the same hostname and same scheme in the next URL, it could reuse this connection again. But in this case, we only have a single URL, so now we're done. So we tell the other side, hey, we're shutting down. And the other side says, hey, we're shutting down too. That's just, TLS speak for shutting down in a graceful manner. And so then we have closed down the TLS layer, and once we have closed down the TLS layer here, there's really not a lot more to do here but to close down the TCP layer, because we created TCP first and then negotiated TLS, and now of course we do the things in the other order. So we close down TLS and now we close down TCP, and then we just send this it's TCP speak then for the same thing. We send a FIN bit and we get an ACK back, and now TCP is pretty much over too, so now we don't have a connection anymore either. And once we've done that, that's still done within libcurl. So once this is done, libcurl libcurl returns into the command line tool, and now the command line tool knows that now this transfer is complete. And each transfer really in libcurl, in the libcurl API, using the libcurl API, it uses handles. So in the curl code, we now close down the libcurl handles that are responsible for transfers. And in this particular case, the libcurl API is called curl easy cleanup. And when we free all the memory, we close all the files, and bam, we're done. And the command line tool then, of course, exit. The last thing it does actually is, of course, it exits, and it exits back to the shell, and we come back to where we started. So that is pretty much the entire loop, starting from sort of clockwise from the top, the command line, the dynamic linker, command line parser, URL parser, when we get into libcurl. And then we resolve the name, we connect TCP, we negotiate TLS, we send the HTTP request, we get the HTTP response and receive everything, we save the data, and then we shut down the TLS, we shut down TCP, and we exit back to the shell. Easy peasy. So that is pretty much what a round of curl does. All of this, of course, explained in this book, Everything Curl, that we try to maintain and update and document all of this as much as possible. So that's what I wanted to tell you about today. So if there's any questions, we could just fire them off. If you have anything in the chat room. So the question is about HTTP 1 and HTTP 2. How many other server types curl handle? So in this particular example, I just showed you doing HTTPS://. That's one URL scheme, right? And curl supports 28 different URL schemes. So you can do transfers using, well, if we call them different protocols, they are 28 different protocols. So you can do, FTP, you can do LDAP, you can do FTPS, SFTP, SCP, Gopher, a lot of different ones, IMAP, SMTP, and things like that. So there are a lot of different things to try with. And a lot of these different schemes often then also support different versions. So for example, you can go with HTTP 1, HTTP 2, HTTP 3, or even you can also go with HTTP 1.0 or 1.1 and so on. So there's really a busload of different alternatives for you if you really want to do that. So curl offers quite a lot of internet transfer abilities. So do I ever get burned out a little bit on working on this for so long? Sure I do. I mean, I don't think I get burned out, but of course my level of fascination or being thrilled about doing this goes up and down. So sometimes I feel a little bit less motivated than other times, of course. I think that's just natural. But typically it comes back, and sometimes I feel a little bit bored, but then I do something else a little bit more, so it comes back all the time, and I still love working on this, and I hope to continue working on this stuff for a while more. Who knows for how long more? I mean, it's been a while. I started on this journey like in late 1996, right? And it's early 2025 now. Okay, so with this, I'm going to end this presentation. Thanks for joining and thanks for asking questions and having fun with me here today. I will do more presentations going forward, of course. Okay, here's one question more. Another question, of course. So what's the process of how curl handles data transfer, including buffering and streaming? Okay. Well, I think that's sort of implied of what I said. So pretty much, you know, in the stream it... Oh, sorry. Wrong. I was gonna do this. So going backwards into this. So if you look at this slide, so pretty much in the... When I'm talking about the saving data over there in the left side, it says save data into the index.html. It is saved in a completely streaming manner. So it'll just get a number of bytes and then save it. Get data, save it, get data, save it. So, you know, that's how you can transfer any amount of data. It doesn't really matter how much data, because it'll never store it in memory much. It'll just sort of streamingly pass it on. And you don't have to save it to a file, right? You can pipe it on to standard out or something, or send it to another program or whatever. So therefore, from curl's point of view, everything is a stream. It always streams. It gets it and just streams it onto something, which usually is storage, but it could be just store it in memory, pass it on to something else. So with this, I'm going to say that there is another question here. So how curl is handling multiple connections in parallel. Curl doesn't do so many parallel connections in parallel transfers. So if you use the -Z or -- parallel, you can do parallel transfers. It defaults to 50, I think, as a max by default. You can bump that up, I think, easily to 300 or something. But curl basically does poll on those, and it does that for the simple reason that poll is very portable, so it's easy to build and run that everywhere. To go really effective, doing more than that, you would go to some socket-based API, and curl provides one of those socket-based APIs, so you can do more than that too. And possibly the curl tool should do that as well at some point, but we haven't done that. We might actually get... If you do 300 really fast transfers, I think we could gain performance by doing socket-based, or sorry, event-based API, but room for improvement. So the eyeballing stuff that you're asking how it really works, I think I explained that. So happy eyeballs, the eyeballing, pretty much means try multiple things in parallel and go with the one that works first. It's slightly more complicated, but that's the easily explained version. Any more? First, second, any more questions? So yeah, and I should just sort of clarify that maybe again, that of course libcurl is used by curl, but libcurl sometimes provides a lot of more flexibility than maybe the curl tool uses. So if you would write an application that would do things similar to this, you could use other features in libcurl, or you could, do more fancy things or less fancy things, whatever you wanted to do for your particular use case. This is just how we've done it for the curl tool. libcurl, the library, provides actually a number of more features and other features than the curl tool itself uses, because of course libcurl is used by quite a lot more things than just the curl tool. libcurl is used by hundreds, if not thousands, of different applications and tools. can you explain how curl uses the Windows API to perform network I/O and file operations? Actually, most of the things we use, both in curl, the curl tool, and libcurl, the library, are using the POSIX-like API calls even on Windows. So in most cases, we actually use very similar code to both Windows and on the Unix-like operating or POSIX operating systems. There are but a few rare exceptions, so there is actually not a lot to say about the differences because there aren't that many big differences. There are in some subtle details, and that you sort of. I used to say that everything in Windows is more difficult and more peculiar than any other operating system because they tend to do their things in a different way than all the others. So you have to sometimes just face those problems and experience those challenges and then sort of solve them. Like, for example, there is buffer size. There's some auto sizing of buffers in the sockets for Windows that we have for some, especially for some versions of Windows. That is really magic and special that we just figured out by experience that we need to achieve really high performance on Windows as well, or at least older Windows versions. But and there are some of these WSA things in curl that isn't straight POSIX, but it's not that much. There are, of course, backends, and there are support for things that are using native code. So there's, for example, support for the S-channel Windows TLS code, library, or whatever you want to call it. So if you build curl to use S-channel, for example, it'll use the Windows native TLS system. And that is, of course, very different than the other TLS backends, but that's a choice you're making, and you don't have to do that on Windows. You can use other libraries too on Windows. So, can I ask if the same programmer does Unix versus Windows development? And I would say so in almost all cases, yes. Because, that's just a fun thing for you to check out the libcurl code, and you will see that basically all code is portable and runs on everything. Maybe not all, but maybe 90% something is sort of just the same thing. So typically you don't have to care about the platform when you write libcurl code. And very, very little code is Windows specific or non-Windows specific. Most of it is just generic C code, which we aim for because it makes it simpler to develop and simpler to write code and simpler to test, because then we can test the code on another platform and just assume that it works on the other platforms. So do we run tests locally or trust the CI a lot? I think we do both. I can't speak for everyone, of course, but I tend to, of course, run a lot of tests locally, but locally is a bit limited, that it's hard to do a lot of different systems and tests setups locally. So yes, we rely on CI heavily. So we have nowadays over 200 CI jobs that build and run curl in many different build combinations and many different operating systems and so on. So it's quite impossible actually to get even close to that combination and that plethora of different build setups locally. So yeah, we have an excellent CI setup that helps us make sure that we at least don't break the important stuff. If we have considered moving to Mason from CMake for build system, well, I think it's sort of build system seems to be what bothers people quite a lot, but I think that's sort of I don't understand why. I don't think it helps anyone to switch to Mason from CMake. I think that's just another build system, and in curl we don't have a problem with the build system. Curl builds blazingly fast. I know one of our contributors now build curl in less than 1 second on his modern machine. You can build curl fast. I don't think the build system is a problem for us, and it's we rather just improve what we have and make sure that is perfectly well to do whatever you want. I don't think switching and we've rather over time recently tried to narrow down the number of build systems we support so that we don't spread out our efforts too much on different build systems, but make sure that we nowadays focus primarily on CMake and AutoTools build systems, and I think that's pretty good. And nowadays our build systems are pretty solid. I mean, sure, we might do something else one day, but I've not seen anyone happy or eager or interested in introducing such a shift, and I don't see the necessity to do that. What's the next big evolution you think curl will see, if any, like the attempt to introduce Rust? In some ways, curl doesn't really do big evolutions. It's more like a constant evolution all the time, and we're just slowly working our way towards the future, and we sort of polish things, we refactor things, we just fix whatever is broken and we move on. We add new things and we move on, and we refactor and remove. Sometimes we deprecate things that we can deprecate, and so I think what we're going to see, I think, sure, introducing Rust, I don't think that's the sort of the right term, because we didn't really introduce Rust. We tried to just introduce a new Rust backend. If we're talking about the Hyper one that we removed recently, so the remote support for, but we support other Rust backends already, and we did it before we started with Hyper. And I'm sure we can support other Rust Hyper backends going forward. Why not? If someone writes a good library and it's written in Rust and we can use that, why not use it? So I think that's good, and I think we're going to just continue doing things in curl exactly as we've done before. So we just move on. We introduce new things, so that we make sure that curl stays with the times, right? If we figure out new things, how to do transfers, we do that with curl. Like we're working right now to introduce support for HTTPS or RR records in DNS, right? Or ECH for TLS and stuff like that. New modern things, how to do network transfers. We want to make sure that curl can do that too. So there's no major revolution coming, and I don't think we ever had any major revolution in curl yet. So how small can curl get if it's statically compile and just supports HTTP2, for example? I don't know. First, it depends so much on the architecture. And so I used to say that you can build, so I have this tiny curl version that I push for people with really small systems. I mean, few megabytes RAM, few megabytes flash. And that one you can build down to around 100K on a 32-bit architecture if you just go with HTTPS support, HTTP1, and just disable a bunch of features too. Like, pretty much disable as many features as you can. Then you can go down to maybe 100K with TLS if you use Wolf SSL. But I think it's hard. I don't think you get quite to 100K, maybe as a footprint, maybe a little bit bigger. And then you basically just add to that depending on what you want. You add, if you want to have HTTP2, for example, you need quite a lot more. You need an HTTP2 library, and you need more features in the TLS library. So then you probably add several 100Ks. And I mean, look at, if you go to a Linux distro today and check how big is curl executable tool, or all the libraries that it includes, sort of dependencies, it ends up several megabytes. So it is somewhere around a few 100K to several megabytes, depending on what features you enable disable. How big build system might be for curl. How many commits? Well, I don't know what you mean. How big build system? The build system, CMake and other tools. I think what complicates matters a little bit for us is that we have curl is very flexible in what features it supports. So you can build it with a lot of features and with very few features and with a lot of backends or very few backends, and it supports a lot of different backends. So there's an explosion of combinations that you can do, and that sort of reflects a little bit on the build system. So it's easy to get a little bit lost in it because we support, I think, around 30 something different libraries on and off in different combinations. And all of that, of course, has to be supported in the build systems. So I think that is what complicates things. Or maybe not complicate, but at least it adds a lot of options and things to keep in mind and keep in your head. Yeah, and how much or how maintenance we do in the build system. I think we do. I don't think I've ever counted how many commits we've done that is build system related, because I've never really thought about that because for me the build system is a way to build the project, and I think it's tightly integrated into the code, so they go hand in hand. They're not really separate in my mind. So I'm sure that we have done thousands of commits that are build system related, but then you also need to remember that I just today, just an hour ago, announced that curl has been built on 105 operating systems, 105, and it's a challenge to find any other project built on more operating systems than so. And a reason or an explanation or how to do that, how to be possible, remain portable to that extent. The build system has to be really flexible, and you have to provide that freedom to all users to build curl on all these systems. So therefore we also cannot, it's sometimes when people are talking about build systems, they make it easy for themselves and they say, sure, we support Windows, Mac and Linux, and we support this build system, and that's very easy. But what if you want to support 15 of those legacy Unixes or 22 of those real-time operating systems, and all of these different flavors of weirdo systems that curl supports? And I think sometimes it's part of the explanation why curl is appreciated, used, and still used in all these different platforms and devices and everything. So that is also a factor. It needs to remain portable and usable in a lot of places. I think, at least. I mean, there's no necessity there. We don't need to. I want to. When it comes to compilers, you need a C89 capable compiler to compile curl, but you can pretty much, if you have a C89 compiler that runs on your operating system that you're using, I'm sure you can build curl with it. Of course, GCC or Clang are the most popular ones, but sure, MSVC on Windows or all the others. Curl is available. I mean, curl runs on pretty much everything you have that has internet connection. So curl runs, libcurl, the library, and curl, the command line tool. Of course, the command line tool is not as many places. Curl, the command line tool, it runs on, in your Windows, on your Macs, on your Linux machines, on Windows, and libcurl is installed in devices everywhere, in all mobile phones, pretty much. iPhone, iOS, Android, most Androids, most cars, most TVs, most printers, most anything that is internet connected has a curl somewhere in there. So we estimate, I say 20 billion installations. I should probably maybe up that counter at some point. But it's somewhere around 20-40 billion. A lot of them, depending on how you count all those mobile app installations. Because in most mobile phones, most people in the, at least Western world, have so many libcurl installations because it's used in numerous very popular apps. So many users typically have curl installed, I don't know, 5-10 times in their phones. So 5-10 times how many billion smartphones are there? 7. So yeah, maybe that is 50 billion installation just in smartphones. It comes to a point when it doesn't really matter. So it's just a sort of a crazy super large amount of installations. So and that's fun, of course, and sometimes a little bit mind-boggling. How do I manage energy motivation when programming and managing projects? It's really hard to say, but I mean, what's fun, and what's not fun is not fun. And I think this is fun, and it's hard to say why it is like that and how I manage to do it. So in my case, I think I've always appreciated development and programming, so that was fun in itself. And I think participating in open source is fun because it gives you context and social environment, so you can sort of find friends and talk with friends. And in a project like curl, there's also a lot of different corners. I think sometimes I just keep up the motivation by doing things in different areas of the code. I can do silly things like changing the output of the progress bar, or I can fill with TCP bits in the connection, or work with something else in the code. So that's what I do. And sometimes, as I mentioned previously, so that the motivation comes and goes a little bit. It goes up sometimes, it goes down sometimes. I don't stress out about it. Sometimes I do something more in another project maybe, and I come back to curl again. Or sometimes I just can't let curl go, and then I spend hours and hours of my evenings on fiddling with things that then in the end don't end up working, and I have to discard it anyway, or stuff like that. So it's just, I have the luxury of doing this as a full-time job, so I also have the luxury of doing it the way I want in most cases, and that makes it work for me. If I have stats on how many current developers are involved and how much each have contributed, yes, you don't know me apparently. I have a crazy amount of stats, graphs, and stuff and numbers. So yes, we know that we, as of yesterday, I think, have 1,332 people who have authored commits that we have merged into Git. We have something like 3,300 people who have helped out, contributors, just reported bugs, helped out with anything. So quite a lot of people, and then people. So how many are we that are maintainers? I think we are 15 persons who have permission to merge code or merge commits into the Git repository, but we're not 15 that are actually doing that. I think we're more like 5 who actually merge code. I think we're around, we do releases every 8 weeks, right? And we're usually around 70-ish contributors per release. So, and out of those, roughly 30 or 40 authored commits. So that's sort of the rate of people we have. I have this graph, number of people who have done 10 or more commits during a calendar year. And people doing 10 commits or more are usually in the ballpark of about 10 or 12 people per year. So that's the set of, the team. I'm the only one who works on curl full time. So all the others are everything from, just single-time committers or part-time contributors in various ways. fun questions. So yeah, the Icing there showed the dashboard link in the chat, so you can just Google for the curl dev dashboard and figure that out. I think there are now 85 different graphs on the dashboard showing different plots for curl development, curl evolution, and things. Are there any upcoming features or improvements in curl coming, and what you're also excited about? I'm actually, I referred to it earlier. I'm working quite a lot right now with HTTPS resource records, which is a DNS record called HTTPS. The name HTTPS is really fun to use in a resource record because it's just hard to find and use. But it's a new DNS record that pretty much, it is used as a way to tell clients, for example, which HTTP versions a client can use, and which so on. It's actually then sort of replacing the old service headers, or maybe and also the HSTS system. So, for example, by looking in that DNS header, you can know if you can try HTTP 3 against the server without sort of doing it any other way. It's kind of I think that's interesting. I think that's a decent way for us to, or for curl users in general going forward, to, in a pretty convenient way, switch to HTTP 3 without explicitly asking curl to try out HTTP 3 the way we've done it so far. So it's I think it's the best way we have right now to slowly transition into an HTTP 3 world. So I think that's pretty exciting. And I think ECH is also cool. ECH, the encrypted client hello for TLS, which is a way to encrypt the SNI field in the TLS negotiation. So the HTTPS resource record, it's not for DO. You can of course use it in DO, DNS over HTTPS. And in curl, we started out with it supported in DO because it's sort of easier to implement it that way. Do you have some of the weirder vintage OSs or boards in possession for fiddling? Well, I have a lot of different weirdo boards and things. I have a lot of systems, but typically I don't use them. I stick to development on Linux as far as I possibly can. And that goes back to the way, and since most of the code works exactly the same, most of the code is sort of written independently of platform anyway. So if it works, if it builds and works on Linux, there's a good chance that it works on all the other systems as well. And if I can just get it to build and work and run the test suite on Linux, and then I commit and make a pull request on, and then I have all those 200 CI jobs. And once the CI jobs are all happy, it's quite likely to work pretty well on most other operating systems too, just based on the way we have designed things and sort of. But it's not a guarantee. And sometimes, of course, if users who are then building curl for operating systems that we don't test this ruthlessly all the time, they sometimes then figure out, of course, oh, something we did a while back actually broke our support for whatever niche system they are using. But then typically they just fix that, send a PR, and we match that, and then it's fine again. So that's pretty much the way we do. We don't deliberately break support for weirdo systems, but sometimes we do that accidentally anyway. And then we just, once we get to know about it, we fix that and move on. So sometimes it's hard to say exactly how well the support actually is for random systems that we don't test all the time. But that's just life. That's the only approach we can have to this. And it typically works really well. And it really, so if I don't really get a benefit for trying out curl on a lot of different weird operating systems. It doesn't really scale for me. So that's why I typically don't even try it on I have a few Macs here on my table. you should see my table. I have a bunch of different machines here. I have a Windows machine, I have 2 Macs, but I barely even log into those and test, because typically I don't need to, and the CI will test a lot of Macs. So yeah, well, Amiga is a great example of one of these niche operating systems. So we had one person a few months ago who contributed quite a few fixes. So, and he made it work on Amiga back then, and we merged his fixes. So ideally Amiga OS works right now, or maybe not. Maybe we broke it again. I don't know. And that's how we go with. I mean, again, back to the 105 operating systems. We surely don't test. I don't think we even test on 10 operating systems. But that also sort of goes with combinations of build options and backends. So we support 12 different TLS libraries, 3 SSH libraries, 3 ways to do resolving, 3 IDN libraries, and so on. 4 different quick backends. So just the combinations, just enter that in a calculator. How many combinations can you do? And then you add different combinations of features, enable, disable cookies, blah, blah, blah. And there's are literally billions of combinations to do. So of course we can't test all that. We just have to make an effort, and we test all the important ones, and we then try to build everything in a decent way to make sure that it is likely that all the other combinations also work. But we can't test everything because it's just not it's not physically possible. Fun questions. And now I've been taking questions for a half an hour, I think, right? So, fire away a few more. What was I gonna say? Going forward, for example, we also talk about deprecating. This summer, we're talking about removing support for 2 TLS libraries, talking about what we're going to change going forward. So we're talking about removing support for the Apple TLS library called Secure Transport and Bare SSL. Both of them being maybe not old, but the Secure Transport one is deprecated by Apple themselves, and both of them only support TLS 1.2 and no later TLS version. So it would be a way to say that going after July 2025, all TLS libraries curl supports, they all support TLS 1.3. It simplifies the messaging a little bit, it simplifies code maybe a bit, and it'll help users get something that is more future-proof when they build curl and they make a selection of what to do, how to do internet transfers going forward. There's been a discussion about the secure transport removal and how to do that, or if we should do that, or if we should postpone that, or otherwise how we are going to support native CA, the native CA store on, I think, primarily iOS devices from other TLS libraries. So that is something I hope we can work on this spring to make sure that we provide that ability to some other TLS backends before we cut off the secure transport. What are our plans for curl to support emerging technologies like web transport and web sockets? And how do I see these technologies impacting the future of HTTP and web development? Okay. First, I don't think WebSocket, I don't think is an emerging web technology. I think that's more of a dying web technology. But anyway, we support WebSockets since a while back. We have a separate API in libcurl even to do WebSockets. So WebSockets is sort of an emerging technology in libcurl at least, and in curl. So that's sort of, I think that's a growing area for curl users to do WebSockets with curl and libcurl primarily. And I think we might see more use of that and more tweaks and polish happening there, so that we improve that support for different sub features and stuff like that, and make it more solid and reliable. But it seems to be one of those protocols that has sort of have a pretty fast curve of new users, so it's already one of the most popular protocols used out of those that curl supports. So even though I think as I said, WebSockets itself is quite an old technology, and maybe at least in some areas people hope to replace WebSockets with web transport, then web transport being done over quick HTTP3 instead of TCP and HTTP like WebSockets. But web transport, we don't have anything for web transport. I'm not sure we will have anything for web transport, because web transport is even more maybe on the I should say it like this. So WebSockets is sort of on the fence. Is it really libcurl a topic for libcurl? Should libcurl really do WebSockets? Because WebSockets is not strictly transfer related. So it's not, well, it is transfer related, but it's not strictly upload download. But anyway, now we support WebSockets, but web transport is maybe even more sort of in that gray area. Okay, maybe. So the discussion hasn't really come up. We haven't really debated what to do with web transport or not. I don't think anyone has actually expressed an interest in working on it, implementing it, and doing all that. And to tell you the truth, I have no interest in that personally myself right now, at least anyway. So I'm not going to work on that unless someone shows up and pays me to do it. So that's where we are with those particular ones. Where are we otherwise? Yeah, I think there might be more to do when it comes to quick and HTTP3 and HTTP versioning internally, and how to do, as I mentioned, how to switch to HTTP3 and so on. So we're talking about that a little bit going forward also. And maybe we have work to do to, I mentioned many times that we have a lot of different TLS backends, but not everything is supported in all these different backends. So sometimes when people switch to another backend, they get surprised because one feature is missing or present depending on which TLS backend they pick. And so of course there's a lot of that we could fill in when there's a blank because a particular backend doesn't support a particular option, but maybe it should. Maybe users want that. For example, recently Debian switched from an OpenSSL build to a GNU TLS build. So they use curl built with GNU TLS as the primary version now, and not the OpenSSL one. And that sort of made an impact to users because now suddenly curl actually works a little bit differently depending on that switch of backend. So that's could be a way for us to make curl a little bit better again on Debian by making sure that the GNU TLS backend for curl supports a few things better. And so on. There's a fun development happening. I'm not sure exactly what's going on there right now, but it's quick in the Linux kernel. So there's an effort to move some of the HTTP3 stuff then into the Linux kernel, and maybe curl should support that then if that ever happens. So there's also movement there. So stuff like that. It's not like we're sort of stopping development or seeing the end in the tunnel or anything in this project. So there's a lot going on all the time. But now I really am going to stop this presentation. Thanks a lot for a lot of fun questions, and I've been yapping about a lot of things in curl, much more than just curl from start to end, or maybe from start to end of from a more bigger perspective. So see you in another talk, stream, presentation, something. Great to have you here. Bye bye.